theory, okay? VSEPR, all right? When you're building molecules, the electron pairs repel each other and the bonds so to maximize the distance between other electron pairs. Okay, so the electrons want to maximize the distance between everything. All right, obviously, the more stuff you put on a molecule, the smaller the bond angles, the less room there is. So that's why it's harder sometimes, depending on the size of the atom, to build big molecules. It takes more energy. Okay, so the structures. A linear structure, pretty straightforward. It's flat. Okay, how do you know if you have a linear structure? You will have a linear structure if there's only two atoms. All two atom molecules are linear. Okay, because that's the most stable distance. So they're 180 degrees apart, right? So all two atom molecules. So that would be H2 is a two atom molecule. It's linear. Okay. HF is linear. Even though fluorine has the electron pairs, the most stable configuration is if it's linear. So anything with two atoms will be linear. Now, there's also three atom molecules. So three atom molecules, but this is the important part. With no lone pair of electrons on the central atom. Okay? So you can have three atoms. It'll be linear, i.e. 180 degrees between the bonds, if there is no lone pair of electrons on the central atom. So this is things like CO2. There you go. It has lone pairs of electrons, but they're on the oxygen. They're not on the carbon. As soon as you put a pair of electrons, a lone pair of electrons, on the carbon, if you did right there, it's going to force the bonds down. Okay? All right, so that anything with two atoms is linear. Anything with three atoms and no lone pair of electrons on the central atom. So anything with like carbon in the center basically is going to be linear if it's got two atoms attached to it. All right, the next one is trigonal planar. Did we have any of those in there? Okay. Sorry? CH2O. Okay. So these are 180 degrees, or sorry, 120 degrees. Okay. How many electrons does a central atom have right here? The way I drew it exactly right there. How many electrons are in a bond? Two. So how many electrons are on that central atom? Six. There's three bonds, right? 2, 4, 6, right? That makes sense? What is the atom that has a central, that is comfortable with 6 electrons on it? Sorry? Boron, okay? So this is when you have a central atom with no lone pair. And three atoms around. say, and so BF3 boron. Boron is comfortable with 6 electrons. It doesn't need any more. It's one of the sub-octet exceptions that we saw yesterday. Even though fluorine has all its electrons, that's fine as long as they're not on the central one. You put a lone pair of electrons on the central one and you're going to change the geometry. CO3 is actually another one. CO3 2 minus. All right. It doesn't have any, it's a carbon atom. It's got 3 oxygens around it, but it doesn't have a lone pair of electrons. Okay. So as long as the central atom does not have a lone pair of electrons and there's 3 attachments, you're going to be trigonal planar. Okay. I'm not asking you to memorize the bond angles. Okay. If you do, that's awesome. But all right. Tetrahedral. Again, 4 atoms around a central atom, no lone pairs. So central atom with no lone pairs, surrounded by 4 atoms. So the most common one is going to be methane. Actually, I shouldn't even draw it like that. That's what it would actually look like. And these ones, the reason I can draw them like this is because they are flat. They're trigonal planar, right? Like they're just a flat molecule distributed evenly. So these ones are carbon and silicon. Silicon are the common ones for these. Silicon chloride is the same idea. Oh, I did a chlorine and the rest oxygens or hydrogens.
Seems like we're all.
There we go. And these, if you look at your periodic table, sorry, I'll put it back up in a sec. Carbon and silicon, group 4. Okay, they both want to form 4 bonds. They don't have lone pairs of electrons. They're going to be tetrahedral. Okay. All right. If you take a tetrahedral molecule and you take away this one atom, replace it with a lone pair, you get a trigonal pyramidal. All right. And what happens is these are 109 degrees, 109.5. If you want to be specific, this lone pair will push the bonds down a bit. I'm not asking you to remember bond angles, but this lone pair just pushes the bonds. They're less than 109 degrees. Okay. So central atom with a lone pair. Surrounded with 3 atoms around it. Attached. So the most common one is ammonia, NH3. If you're going to do the it would look something like that. I'm not exactly sure how I'm going to test this, but make you memorize all these. I don't know if I want to do that. I don't know how much that adds to our knowledge of chemistry. All right, and then if you take a trigonal pyramidal and you take another atom away, take another atom, put another lone pair, pushes the bonds even more, and you get bent or angular. Okay. So this is a central atom with two atoms attached and at least one lone pair on the central. All right, and instead of that.
Is Tesla something like the definitions of the...
Yeah, I'm not sure what I'll do. Okay. So the most common one here would be water, H2O, which is like that. And you can see the bond angle. Look at the bond angle here. With one lone pair of electrons and two atoms attached, it's 120-ish. If you add another lone pair of electrons, it shrinks it to less than 109. So repels each other. Okay? And that would be an SO2 molecule. So if we have SO2, a good question that I could ask would be, which of these angles is smaller? Which angle is smaller? Water or SO2? This angle here. Okay, so which angle here? So if I said, would this angle or this angle be smaller?
I would say water,
The water. Why the water?
because it has more electrons pushing.
4 electrons. That would be something I'd want you to know. Like that tells me you sort of understand this whole idea of VSEPR is the more electrons that are here pushes the bonds together. This only has one lone pair of electrons, so there's less pushing the bonds. Okay? And we're almost done. We'll just do these last two. We already talked about these yesterday. Trigonal bipyramidal. All right? Phosphorus. What's 5? Heptachloride? Heptachloride? Penta. This is a covalent molecule. Pentachloride. So things are getting squished. You have two different bond angles. I'm not asking you these. These are 90, but the ones on the side here have a difference of 120. And you have sulfur hexafluoride. Same idea. Everything's 90 degrees in that. Yeah, sulfur and phosphorus can use the d orbitals to increase. I'm going to stop there today. Tomorrow, we'll look at molecular polarity. So we talked about bond polarity, how the charges are separated in a bond. Now we're going to look at what that looks like in an actual molecule. And that depends on the 3D shapes. We're going to have a quiz, not tomorrow. I think I'm going to, what day is it, Wednesday? I think we're going to have a quiz Friday. I haven't decided what type of quiz that's going to be. I'll let you know tomorrow. Okay.